Hi there. In this section, we're going to continue on with Chapter 6 and look at the natural exponential function e to the x. So let's jump right in. So you guys have seen this function before, and it was probably used when you learned about compound interest. That's when it's normally introduced, but we're going to see that it does lots and lots of different things. So the way that we define the exponential function, again, it's called the natural exponential function, meaning like the default setting is e. It's just the inverse of the natural log. And as we saw, the natural log does arise naturally as just the area under the curve of 1 over t dt. So the idea is that if we use cancellation equations here, that e to the natural log of x is x, and natural log of e to the x is x. So what does that mean? Well, it just means that if we're trying to get x outside, like if we're trying to solve for x, that we can just take both sides of an equation and raise it as a power of e. We call it exponentiating base e. And down here, if we're trying to solve for x, we would just take the natural log of both sides of an equation. And that's how you use the cancellation equations. So first thing we're going to do is find the inverses of these functions. And we're going to use the tried and true method of section 6.1. So you write your equation as y equals, swap x and y, and then we solve for y. From here, it's a relatively straightforward exercise in algebra. And at the end, you take a natural log, right? So multiply both sides by 1 plus e to the y. Distribute. Now we need to get both y's together. It doesn't matter what side of the equation you do it on. So I just brought the e to the y to the left and brought the x to the right. Next step, factor the left side. Next step, divide by x minus 1. And an algebra thing happens here. Because this x was negative, we'd prefer to get rid of this negative. So just switch the denominator and then take the natural log of both sides and you're done. So I'm not going to show, you're done. I'm not going to show cancellation equations, right? Those were shown earlier, but just I'll notate that over here that I'm using cancellation. So the natural log of e to the y is just y. That's the definition of e to the y, right? So we say, what is this e to the x function or this e to the y function? Well, it's the function that if you take the natural log, you get x. Okay. So don't worry too much about the mechanics of it if you forgot from college algebra or high school math. Don't worry about it. For now, this is how we're defining it. Why does it work? Because we defined it in such a way that if you do this action, you get this result. It's what we do in math. So pretty cool answer, as you can see. And if you graphed both of these functions together, you would see that they are mirror images around the line y equals x, as we saw in section 6.1. Let's do the next one. How do I find the inverse of y equals natural log to the fifth? So take the fifth root of both sides. Again, another cancellation equation thing. I'm just not showing it, right? Then exponentiate both sides. So here, this is just e to the y to the fifth, e to the y to the 1/5, which is just the fifth root of y. And if you exponentiate natural log of x, you just get x. That's the answer. So this is just a brief introduction to using cancellation equations with e and natural log x. It's not like a college algebra class where we spend, days and days on this kind of stuff. Couple examples. If you need more review, consult a college algebra textbook, or of course, look at any of the online resources I provide at the end of the notes. Because you do have to be able to work with natural logs and exponentials for the entire rest of the class. We don't spend a lot of time on it. We just throw up some rules, prove some theorems, and then we're off doing other stuff. So here we're going to do more cancellation equation stuff, but here we're solving equations. We're not finding inverses, we're solving equations. So let's jump right in. So the first one is natural log of 3x minus 15 equals 5. First thing I have to do is exponentiate both sides. So it cancels on the left side, just whatever's on the inside is just the only thing remaining. And on the right, that 5 becomes an exponent. Remember, the natural log function we've proven is increasing in 1 to 1, which means it has an inverse. That means the exponential function e to the x is also 1 to 1. So when we exponentiate both sides, that function is also 1 to 1. So we're allowed to do this. Add 15 to both sides, divide by 3, and you might want to simplify a little bit. So that's what I called the answer. On the homework, if you typed this in for the answer, it would probably be fine. But it's always good to simplify this kind of stuff, just because things might cancel. All right, let's look at the next one. So here we have e to the 5 minus 3x equals 10. Here, first steps, take natural log of both sides. Cancels on the left side, and we get a natural log of 10 on the right. Again, this is 1 to 1, so we're allowed to do it. I swapped the natural log and the 3x. Now, I'm trying to solve for x, so I just divide by 3. This one doesn't simplify nicely, so I just left it alone. So nothing too fancy is going on with these. You might need to be able to do this if you're required to find critical points and things of that nature, where you have to set things equal to 0 and solve and that kind of stuff. All right, so here's our properties of the natural exponential function. Again, I'm just going to call it e to the x. Here we go. It's increasing. Domain negative infinity to infinity, range 0 to infinity. And it has these two interesting limits. So we haven't done anything with exponential functions yet, so it might be hard to see why this is true. So this is the kind of thing where you could use a graph, you could use a table to see that it's true. Remember, we don't have any proofs for this kind of stuff the way we do for polynomials, right? We don't have a theorem. Well, we have the theorem for polynomials. 1 over x to a power, the limit is 0 as x goes to infinity. We don't have anything like that. So to prove that this is true, you'd have to just use a table and plug in bigger and bigger negative numbers to show that it's true. And then here, this definitely makes sense that it's true, right? So e to a larger and larger power, e is bigger than 1. So any number bigger than 1 to a large power is a large number. So let's do a couple of these, see how this works. So here we have an interesting function. This function is e to the x over 1 plus e to the x. And we're going to investigate its long-term behavior on both sides. What happens as you go to the left and what happens as you go to the right. We're going to do it with algebra. We're not using graphs, not using tables. So let's start going negative infinity. So if the limit exists, my limit laws say that I can just distribute that limit inside everything. So we know what this limit is, right? This is 0 and this is 0. Well, 0 over 1 plus 0 is just 0. So that limit is just 0. But what happens if we go the other way? So here, when we go to positive infinity, I went ahead and did the step for you, but I just want to show you where it came from. If you try to plug in infinity here and here, you can't use the limit laws, because these limits don't exist. This would be infinity over infinity plus 1. You're not allowed to distribute those limit laws inside that. We have to do some manipulation first. So I'm going to multiply top and bottom by e to the minus x. And then it gives me this expression, right? E to the x times e to the minus x is just 1. This 1 distributes, and then we have the same thing here. Now, I can just reverse the signs on this thing. Okay, so this is the same thing as saying, this says, as x goes to infinity, e to the minus x. Well, I can change this, x goes to minus infinity of e to the x. So that's a cool little trick that you're allowed to use. Again, I can't really use it over here because I hadn't manipulated this yet. So this is kind of like the logic you need to use. Now, I just use the same trick as up top. Oop. I use the same trick as up top. I push those limits all the way through. and I get 1. And if you graph the function, you'll see that it's indeed true. So this function is what's known as the logistic function. For those of you moving on into more advanced math, you will see variations on this quite a bit. It's used to model things like population expansion, spread of disease, circuits, and it really has a lot of uses. All right, moving on. So this is a great trick. If this is on a test, you pretty much got to use a trick like this. So these are more laws of exponents. We saw them earlier in different contexts, but here they are in this context. So a, x, y, and r are real numbers, and a has to be positive. So adding exponents is the same as multiplying the functions. Subtracting is the same as dividing. And if we have a to the x to the r, it's a to the xr. What I want you to notice here is these correspond exactly to the logarithmic rules, the laws of logarithms, right? Except the laws of logarithms start on this side and go back the other way. So we'll be using these properties to do some proofs. First one we want to talk about is the fact that e to the x is its own derivative. So this has a lot of meanings, right? And you can see why we call this the natural exponential function, right? Derivatives appear naturally all the time in science. So if you can find something that's sort of its own rate of change, it is its own rate of change, you kind of calibrate everything right at that level. And that's what we've done. So let's prove that this is true. So we're going to say y equals e to the x. Now I'm going to take natural log of both sides. Now I'm going to use implicit derivatives. So I don't know if you guys remember implicit differentiation, but it just means anytime you take a derivative where there's an x, you ignore it. Anytime you take a derivative with the y, you tack on a y prime. Here we multiply both sides by y. This is telling us the derivative is the function, so the derivative is e to the x. Pretty easy proof. So you can see that we're using a lot of the techniques we've established in the class so far. So the derivative of e to the x can be combined with the chain rule, and either one is fine. Either version that you want to use is fine. So d dx of e to the u is just e to the u du dx, or if you prefer the g of x notation, it's just e to the g of x times g prime of x. Either notation is fine. We use both of them, obviously. This is used more often when we go backwards and do u substitution. But if just as a flat derivative formula, this one works fine. So let's go ahead and do one of these. Find y prime if y equals e to the minus 4x sine of 5x. So I'm just going to take the prime of both sides, right? Take the derivative of both sides. On the right side, that is product rule. So I just write everything out with the product rule. Take those inside derivatives. Those inside derivatives both have a chain rule. And then just simplify it as much as you can. What I did here is I factored out the e to the minus 4x. This is a very common tactic, especially for those of you moving on to more advanced classes. When you guys get to differential equations, you will see more of this stuff than you've ever seen in your entire life combined. Generally speaking, you want to factor out just common factors, because we might have to find critical values, or we might have to find, maximum and minimum values. Whereas this thing can never be 0, we can find where this thing is 0. So just get it nice and factored, plus it's easier to type in. And there's your answer. So on a test, you pretty much got to show a lot of work. You're not allowed to go straight from here to here, because there's no way you can do it in your head. So speak of the critical points, here we go. So we want to find xy. Our function is x e to the x. Then we're going to use the second derivative test to verify that this is a local minimum value. And then we want to show that this value is an absolute minimum. So a lot of stuff going on here. We're using techniques from all of the chapters so far, except chapter 4. So first thing we do is take a derivative, product rule. It simplifies real nice. And then I went ahead and factored it. So I set it equal to 0, but I factored it just because, look, if you're trying to solve this and setting it equal to 0, you're running into trouble. It's much easier to factor it. Now I know where this is 0. E to the x is never 0. So x plus 1 is 0 when x is minus 1. So x equals minus 1 is the only critical value. So you can see why factoring is important. So on a test, this would be fine to leave it like this, but it's still a good habit once you start getting to here to start simplifying everything. Okay, so we found the critical value. There's only one. But we need to show that this is a local minimum. So in order to do that, oh, here's the y-coordinate. Sorry, I forgot. Here's the y-coordinate. So here's the x and y-coordinate. Now let's show that this is a local minimum using the second derivative test. So the trick I'm going to use here is I'm going to distribute this derivative because we already found this derivative in the previous problem, or in part A, and we know what this derivative is. So it makes that really easy. So this is an example where you don't want to have to do a problem twice. Use what you have. So this is like a strategy for solving. I already know what this is, so I split the derivative in two, compute each derivative separately, then I can combine it back together. So this is just x e to the x plus, so this will be 2 e to the x. Again, factor out the e to the x. Now, I need to show that this value is always positive, right? So I plug in my critical value into my second derivative, I get a positive number. That means that this, where's the original function? It means the original function, oh, here it is, x e to the x is concave up everywhere. And if it's concave up everywhere, that means the local minimum, the critical point is the local minimum, right? So it's concave up everywhere, so it comes down like this. The only place the derivative is 0 has to be a minimum, because it's concave up. So that tells us that this is a local minimum. So how do we know that this is an absolute minimum? Well, the only place that an absolute minimum can occur is a local minimum or an endpoint. And there are no endpoints because this, our function x e to the x, its domain is all real numbers, and there's no endpoints to check. So because we found it's a local minimum, it has to be the absolute minimum. So this looks similar to some stuff I did in chapter 3, but you can see how it applies here with some of the new stuff. All right, so there you go. That was a pretty interesting example. Again, this is the kind of stuff you're going to have to do on a test. Make sure you can do these problems. So the integral of the exponential function is itself plus c. No need to prove this. This follows directly from it being its own derivative. So let's do an integral and see how this works. So you're looking at this problem and you say, I don't have a rule for e to the x cubed. You have a rule for e to the x or e to the u. So maybe this is a u substitution. Which function here is considered the inside function? Well, it's got to be this x cubed, because when you take the derivative, this kind of looks like this x squared. So you keep fiddling with this until you get an x squared dx. So here's this, and I just moved the x squared over. So now you can kind of look at it and see how everything works. So here we have e to the u, and then x squared dx is 1/3 du. Let's just plug everything in. And as is normal for me, I pull the 1/3 out front. Now it looks like something I know how to do. This is just 1/3 e to the u plus c. Plug u equals x cubed back in, and you're done. And again, check your answer taking the derivative. I'm not going to do it for you, but make sure you can do it. So all of this u substitution chain rule, u substitution chain rule, u substitution chain rule. Just got to keep practicing it and keep practicing it. All right, let's keep going. Last one. This is sort of a challenge problem. And this is really just indicative of the kinds of things that you're going to see moving forward. For those of you moving on to Calc 2, problems like this pop up real early in Calc 2. So if you guys are taking Calc 2, don't wait. Take it in the fall while you still remember how to do integrals. All right, so we're just going to look at it and say, what strategy do we have? Well, we think it's a u substitution because we don't have a rule for something that looks like this. It doesn't look like I can simplify it. So what you have to do is you basically have to take a leap of faith and pick something as your u. So, could our u be e to the x? If you do that, you're stuck with a 1 plus u in the denominator. That's not good. Could it be e to the 2x? Well, that's an enumerator. Remember, you don't want to really pick a u in a numerator. So instead, let's make it 1 plus e to the x. Even though you might think, well, where'd that come from? You have limited choices here, so just pick whatever you can and see what happens. So take the derivative, we get e to the x dx. So now you attempt to rewrite this to match these pieces up. But you have to notice that we are going to have an extra e to the x in the numerator. We're going to get 1 from the du, but we're going to have an extra one here. So you have to solve this thing for e to the x. So it's actually going to be u minus 1. So watch how this works. So I split this into 2, right? So e to the x times e to the x is e to the 2x. This is my du. This is going to be u minus 1, and this is going to be u. This simplifies. And I know how to do this integral, right? So the integral of u is the integral of 1 is just u. Integral of 1 over u is natural log of absolute value of u, don't forget the absolute value, plus c. Plug 1 plus e to the x back in. And believe it or not, we're not done. So where did this 1 go? Now we're done. Where did this 1 go? Well, one thing you want to notice is that it got absorbed by this c. This is a constant, so it turns out that any constant you put in there, it won't matter. If you guys want to try this problem with u equals e to the x, it'll also work, but you have to use what's called partial fraction decomposition to get to here. I don't recommend it. So you do a little bit more work up front for this problem, but everything else works out real nice. One other thing I want to point out. I got rid of this absolute value. 1 plus e to the x is always positive. So you don't need the absolute value anymore. And that's important, okay? So you guys got to constantly be simplifying, constantly be thinking about how does this answer match up with other things, you know? Am I making this as simple as possible? Because I don't know if the homework will accept this with an absolute value. I just don't know if it would. All right, well, that's the end. If you guys have questions, let me know, as per normal. And this will be the last section on exam 4. But there's more videos coming. We have a few more sections to go that will only be on the final exam. And I will see you guys next video. And let me know if you have any questions. Bye-bye now.